Let's look at vectors in 3D. So again, we're taking it from the two-dimensional idea, pushing it through to the three-dimensional idea. We talked about unit vectors. Okay? Remember, every vector has the corresponding unit vector with the same direction. So the actual formula is the same. It doesn't matter whether it's 2 dimensions or 3 dimensions, 4 dimensions, 5 dimensions. We could keep going if we wanted to. It's still the same idea. If you want to find the unit vector, remember the symbol for the unit vector is the caret symbol above the vector, then it would be the vector divided by the length of the vector. There are 3 special unit vectors now because we're dealing with 3 dimensions. Okay. All vectors can be written in terms of its components, same as in 2 dimensions, as long as we pick these components that are orthogonal. That basically just means mutually perpendicular. So each one of them is perpendicular to the other 2. Well, we've got something that does that, and that's the Cartesian space, because the x-axis and the y-axis and the z-axis are all perpendicular to each other. So it's convenient to use that when we're resolving vectors. Same as we did in 2 dimensions. We used the x and the y-axis. We resolved it into that. In the x direction, I. Same as in 2 dimensions. In the y direction, j. But now we have a third one, which will go in the z direction, and amazingly, we call it k. So we'll have I, j, and k now as our 3 special unit vectors that we're going to use. So how do we write the component form? Whoop, there's our space. Let's put it in a vector. So OP, P's got coordinates, x, y, z. I'm calling that vector U. Now, position vector, remember we write it as OP with the arrow on the top. Nothing has changed, we still do it that way. But now, it's an ordered triple instead of an ordered pair, so x, y, z. Our vector, we still do it as a vector, x, y, z. There's now 3 numbers in our column vector. And if I break it in the component form, then it'll be x times the I vector, y times the j vector, z times the k vector. So again, everything transfers nicely from our 2-dimensional idea. And if I have to find the length of the vector, well, that's the distance formula we just talked about. So square root of x squared plus y squared plus z squared. So let's have a look at this little problem then. ABCD is a parallelogram, but it's actually sitting in 3 dimensions now, rather than in 2. We know the coordinates of A, B, and D. There they are. First thing they want us to find are the vectors AB and AD. Again, nothing has changed. We want to find the vector head minus tail. So AB would be head, 18, 4, 8, minus tail, 4, 2, 3. You see, I think column vectors, certainly once we move into 3 dimensions, is the nicest way of playing with these, because now it's real simple. I just read across the line. 18 minus 4, 14, 4 minus 2 is 2, 8 minus 3 is 5. There is the vector AB. AD, same idea. We get minus 5, 10, 10. Find the coordinates of C. Okay, so what do we know? It's a parallelogram. So I know opposite sides are equal and parallel. In other words, they are the same vector. So the vector AB is the same as the vector DC. So C minus D is equal to B minus A. We're trying to find the coordinates of C, so I'll move the D over, and I'll just substitute in the vectors that we know. So it's B minus A plus D, read across each line, and we now have 13, 14, 18. Haven't answered the question yet, because that's the vector. The question asks for the coordinates, so it's 13, 14, 18 is the point C. Division of an interval. Here's an idea that was in the old course in 2 dimensions. For some reason we don't do it anymore in this course, but it's still an interesting thing to look at. If you want to divide a line into intervals. So we know midpoint, of course. That divides a line in the ratio 1 to 1. But why 1 to 1? I mean, we can divide it in any ratio we like. So let me explain what a division of an interval is. Here's an interval AB. Now P divides it in some ratio. So I would say, well look, P divides AB internally, because it's between the 2 points, in the ratio m to n. Now the order is important. Because I've called the interval AB, then the ratio mn means that the distance AP would be the m parts, and the distance PB would be the n part. So I could have said P divides BA in the ratio n to m, but the actual naming is important. What's an external ratio? You see, you could extend the interval out to the point P. We still say P divides the interval AB, but we say it divides it externally. P is on the outside. So if P was to divide AB externally, still the same idea, the distance A to P would be M parts, and the distance B to P would be N parts. Just now means it's on the outside rather than on the inside. So if P divides AB in that ratio, then using vectors, if we're now talking about that interval as a vector, this is how we would do it. The vector P will be NA plus MB divided by N plus N. So whatever the ratio is, M and N, they're added together. We're going to divide this new one by that amount. And it's like the ratios swapped around, because you see how N's now with the A and M's with the B. So it sort of swaps it. Let's do an example and make it a little bit more obvious. So we want to find the coordinates that divides this interval in the ratio 1 to 3. It's the ratio 1 to 3. So I'm dividing by the two numbers in the ratio added together. So you'll notice 4's on the bottom of both fractions. But then the ratio was 1 to 3, so you see how I've swapped the numbers around. It's now 3/4 on the first one and 1/4 on the second one. So basically swap the numbers, divide by what they are added together. But make sure you write the vectors in the correct order. And now all we've got to do is work out what that is. There it is, 1, 9 on 2, 3 on 2. But again, it said find the coordinates, so P would be the point 1, 9 on 2, 3 on 2. Let's do an external one. What's the difference? External division can be thought of as a negative ratio. So we do exactly the same thing, but we just make one of the numbers in the ratio, and it doesn't matter which one, but we make one of the numbers in the ratio negative. So 5 to 2, I've made the second one negative. I'm saying it's 5 to negative 2. Could have done it negative 5 to 2 if I wanted to, doesn't matter. So let's set it up. Bottom of the fraction are the two numbers added together, but now one of them is negative. 5 and negative 2 is 3. So we have 3 on the bottom of the fraction. Swap the numbers around, so the first fraction becomes negative 2/3, the second one becomes positive 5/3. Just do a bit of calculation, and there's our vector. Notice this time I've left it as a vector because it said find the position vector, not the coordinates. All right, that will start us off.